really, this is about Professor Mike McCarthy, who is the Henry
Samueli, right,
Samueli
Broadcom, yeah.
Professor and Director of the Center of Engineering Science and Design at UC Irvine. As some of you know, Mike was here at Penn in his formidable years as an assistant professor in mechanical engineering, and we were very, very sorry to see Mike go. This was at a time when the GRASP lab was really trying to find its feet and foundations, and Mike was quite significant in the GRASP lab and some of the early work with Ruja Baichi, and Norm tells me that he also had a grant with Mike. He's been very prolific, has over 200 publications and 5 books, including Geometric Design of Linkages, that I think he'll tell us a little bit about today, and a number of honors and editorial boards and so on, but let me leave you to Mike.
Thank you very much. Thank you for having me. It's a pleasure to be here. It's been really a wonderful opportunity to be back here at the University of Pennsylvania. So I left in '86, actually had family issues, parents who were not well, and so getting back to California was an urgent issue at the time. But apparently it was okay because they hired Vijay Kumar to replace me. That's my understanding. So, I think it's okay. What I'd like to talk to you about today is the design of linkage systems to draw specified curves. Okay, this is a very classic problem, but I sort of want to but the kind of work that we do is we actually try to compute designs. You give me the specification of what it is you want to do. We want to compute the device that does it. This is most easily understood when you think about, well, give me a curve. I've got a curve. Give me a device that draws it. And that's where this comes from. But I wanted to take a minute to sort of put it in the context of what we think of as design these days. Design is, the sort of MIT version of design is represented here. There's all of this stuff that has to go into the design process ahead of time. We come in right here in the creative design process. You have to already have decided what your task is. And then we represent it mathematically and then have the computer do calculations that address the mathematical constraints and give you options, and we also evaluate them to make it relatively simple. When we do calculate classes of linkages that designers are not able to conceive on their own at this point in time. In the Stanford model, they have essentially the same pieces, but they represent it differently. We come in at the ideation or prototyping stage. That's what we're talking about. Probably the most famous example of this is James Watt's approximate straight line motion. This shows up in the steam engine as this device right here, which is then connected to a pantograph. That guides this point in a straight line, and that straight line allowed the double-acting steam engine. It meant that you could not only push on the piston in one direction, you could reverse it and push in the other direction. That increased the efficiency of the steam engine by 70%, made the steam engine practical in other applications rather than just pumping in a mine. They now put steam engines everywhere, on locomotives, in plants, on boats, and it was that device right here that moves in the straight line that made that possible. It became very interesting to mathematicians to try to come up with other devices that drew straight lines. So this is Chebyshev, the Russian mathematician, came up with this device. Roberts was a famous mathematician, and these are all in the 1800s. It turns out that there is, in fact, a device that draws a pure straight line, this Spatial mechanism. Now, what I want to draw your attention to are these two devices. These are presented in Kempe's book, How to Draw a Straight Line. And it's a very nice lecture that talks about what was known about drawing straight lines at that time, about the 1870s. This mechanism draws a straight line, but it also moves this device in a pure rectilinear motion. This moves in a straight line, but it also moves it in a pure rectilinear motion. So these were things that were known in the 1800s. Kempe went even further. In this paper, he says, and what he does, let's see, Kempe showed it's some argument over whether he proved this or not. But he basically showed that you could calculate from any algebraic curve a sequence of mechanical operations that would ensure that this device, which is for our purposes just a 2R chain, he drew it as a parallelogram, but it's just a 2R chain. We know that the endpoint of a 2R chain could trace any two-dimensional curve within its workspace. He said that I can use this equation to constrain these two joints of the 2R chain so that it draws this curve, this plane algebraic curve, exactly. Now, he admitted that the method, however, is of interest, showing that there is a way to do it, but he admitted that that his current method wasn't practical. Now, this became this was in the literature for a long time, but it became the focus of a lot of work in the early 2000s when it was actually proven. It took a little bit extra work. They have a whole bunch of cases that they addressed that Kempe sort of ignored, but they basically proved that Kempe's statement is correct, that a real algebraic curve, this polynomial function, that there is a linkage that will draw that curve. In fact, it's been generalized by other people to be piecewise continuous algebraic curves, to curves in 3 dimensions, 4 dimensions, and what they get is a device that is fairly complicated. Okay. In fact, terribly complicated. Okay, so complicated that it's just at this point in time, it's a mathematical curiosity. Now, in the early 50s, Freudenstein took a different approach to path synthesis. So rather than trying to draw the continuous path, what he did is he says, well, I've got a 4-bar linkage. 4-bar linkage draws a particular type of path that I understand. Maybe I can get the 4-bar linkage coupler curve to match the path I want, and the way I'll do that is that I'll set up the equations and calculate the dimensions of the 4-bar linkage. So this was done in 1963. It's known as the 9-point path synthesis problem. So you give me 9 points on a path, I can design a 4-bar linkage that fits those 9 points. So if those 9 points are selected appropriately, then the coupler curve will fit your desired curve. This was picked up in 1992 and as an opportunity to test what were then beginning algorithms that would solve all of the roots of large systems of polynomials. This was done on a 7090 with it cost $3 million, 36-bit computer, 32K memory. This was the challenge that we were working on in those days. It's really astonishing when you compare the computational power that we have today to really bring to bear on these problems. Even back in 1992, they were working on an IBM 3081. They formulated this problem. It's the 9-point path synthesis problem for a 4-bar linkage. And what they found is that in order to get all of the solutions, they had to solve 20 quadratic polynomials, which means that with a simple calculation, you just multiply all the degrees of the equations, you get 20 to the 20th power. It says that there are at most 1 million roots. There's no more than 1 million roots, which is a good thing. But in this case, there's quite a bit less than 1 million roots. There were 200,000. So your computer has to now track all of these points. Using homotopy techniques, we can do that. It took them several weeks of calculation, but they solved it, and they found all of the solutions, and they showed that an arbitrary 9-point path synthesis problem has 1,440 solutions. All right. What I'd like to now show you is what is the simplest of the unsolved problems that we have in kinematics, okay? And this is nothing more than taking that problem of Freudenstein's and generalizing it to not a 4-bar linkage, but a 6-bar linkage. The 6-bar linkage differs from the 4-bar linkage only in that there's 2 loops rather than 1 loop. So you have 2 loops here. There's a 3rd loop when you sort of include the 2. All the 3 loops are linearly dependent. But in order to solve the path synthesis problem, and we were working on this problem because we wanted to develop a leg brace that would track sort of natural walking movement. So we would take the the motion capture of how a person walked, and then we tried to design the brace so that it would match that motion. Winds up, you have to solve these set of loop equations. So this is the way we mathematically formulate the problem. Nothing more than vector around the loop. We use complex numbers just because it's easier. Vector around the loop. And so these are the vectors around each of the 3 loops. It is known, it's actually easy to calculate that you can fit 15 points, not 9, 15 points with this set of equations. You get 154 quadratic equations and 154 unknowns. The total degree of the system is 10 to the 46th, which is an enormous number. It is just not possible to compute those, okay? Simply not. Now, I showed you before that the million simplifies down to about 200,000, and it's expected that the geometry of this problem would simplify it down by about the cube root, so it would get it down to about 10 to the 15th. But that is still a gigantic computational problem. So this is the simplest unsolved problem we have. All right? What I now want to show you is the most difficult, the most complicated solved problem that we have. Okay, the way we do this, what we're solving now is instead of tracing a trajectory, what we're going to do is we're going to coordinate the input and output functions of two linkages. So what we'll say is that I want to design this device so this output is a prescribed function of this input. Now again, we cannot fit a continuous curve, so we're going to fit it at a discrete set of points. All right, what we can do, we wind up having to solve this set of equations. The difference between this set of equations and the previous set is we only, in this case, have to solve 2 sets of loop equations, not 3. And what you get is that for n discrete positions, you define the function by sampling it at 11 spots, you get a Bezier bound. It's Bezier's theorem that tells you that you can multiply the degrees of all of these equations. You get that the Bezier bound is 10 to the 21. Again, an enormous number. However, it's computationally tractable to actually go after this set of numbers, and you find that the multi-homogeneous degree is 10 to the 6th. This we can compute. Okay, this we can't, but we could massage it enough to find out. We could massage these equations enough to get that the multi-homogeneous degree is 10 to a million. We can work with 200 million paths. 30 hours of computation time on 256 nodes of a high-performance cluster. That's not a lot of computing, but that's, it turned out that's what we could get, and people left us alone, and we just let it go. We were able to solve this. And it has so far given us the largest solved problem in this area. Now what we did is we want to do the path synthesis problem, so we modified the path synthesis problem in the following way. All right? We'll specify a 2R chain just like Kempe did. We say we want it to pass through a curve just like Kempe did. We sample that curve at 11 positions. We now do the inverse kinematics to get the joint angles. And we design a linkage that coordinates those joint angles. Okay, so essentially what we're doing is we're doing mechanical programming of the path of this linkage. That turns out to work. It works remarkably well. Here is an example of a walking machine. This is, why am I blanking? Jensen. Theodor Jensen. He's an artist in the Netherlands. And what he does is he builds these gigantic walking machines. One of the ones that he also, they're known as the Strand Beast. He builds them out of bamboo. They're on the coast of Amsterdam. They use wind power to show them walking along. They're very beautiful, very elegant. This leg is what we're talking about here. So here is the leg here. It's an 8-bar linkage. Okay, and this is the path of that 8-bar linkage. Okay. We're going to sample it at 11 points. And we're going to design a 6-bar linkage that accomplishes the same movement. And there it is. So we get what he used 8 bars to design, we're able to get a 6-bar linkage to design. Now we can do more. For this, because of the procedure, we get a lot of solutions. So we can actually vary the path, and we can explore a whole range of different walking legged systems, different gaits. We can look at different linkages because we have solved this set of equations. Let me see what they look like.
At different points, you would get different solutions.
Yes. Yeah. Yep. It's depending on how you define the curve. They'll be related, but we haven't studied that. We don't exactly know how they're related. Daniel Lee was asking me that. Can we categorize things? Can we use machine learning based on this to actually sort of identify clustering? We see clustering, but we haven't been able to identify it. We're so happy when we actually get a design. We continue on. Okay, so this particular example, we took the linkages, we linked them together, we made it out of polyethylene, and then we have our little walking robot. So that's a single degree of freedom mechanism. One motor drives all 6 legs. This gives you a little heads up on our, I've done a lot of theory, I've done a lot of software. I'm still developing my manufacturing skills. I wish I had the lab you guys have down there. It's absolutely beautiful. All right, this is another example of that application. This is a jumping robot developed by Mark Plesnik and Ron Fearing using exactly this theory. So this is their, it's got a name. What? Sultan? Salto, that's exactly right, the Salto jumping robot. So it was in Science magazine. So he did this. And what you can see here is what he's doing is actually programming the velocity at these various points and then designing the 6-bar linkage. Because this 6-bar linkage has the same topology as the original one that we ran the 300 hours of computation, we can use the same solution and just use a parameter homotopy to look at and explore these other designs. Okay, but let's back off a little bit. Let's now let's go back to Kempe's theorem, and let's think about what Kempe was doing. These are Kempe's devices that he introduced to perform operations, mechanical operations, addition, multiplication. This he calls a translator, which means that he just moves an angle from one point in space to another point in space because he's going to add angles. This is an adder. This will add 2 angles that are located at the same place. This will multiply the angles. But if you now take those and you say, well, what would I do if I had to make an addition, a mechanical addition operation, what would I do? Well, it's a bevel gear differential is their simplest example of an adder. A pulley or gear train will do multiplication. It'll also do translation. So if we just ask the simple question, well, what happens if I just simplify Kempe's theorem? Can I get something that's a little bit more practical? Sort of the inspiration of this, by the way, was the computer, the mechanical computers that were well established into the 1950s that rely entirely on mechanical integrators, mechanical differentiators, multiplication, and addition. These were very sophisticated devices that existed right up until the mid-60s and 70s. All right, so this is the result of that. Okay, so we go through the same calculation. We start with our to our serial chain, which is sitting up here. We transform the equations into projections on the x-axis. That's Kemp's trick. And now we introduce mechanical adders, and we use multipliers, and then we use pulleys just to move the data around. This turns out to be the serial chain that you get when you write the algebraic equation out. You get what can be interpreted as the equation of a serial chain. To get the condition that it is a algebraic curve, you simply constrain the end of the serial chain so it moves on the x-axis and on the y-axis, and that's the entire essence of Kemp's proof. This is what happens. If you do the traditional approach, this is the kind of things that you can find on the internet showing how to draw this cubic curve. So a cubic curve, this is an elliptic curve, symmetric about the x-axis, so you're only seeing it draw. I don't know if you saw this point moving. Let me just run it for you again. Oops, no, that's my curve. Okay, so this is our curve. And here we are tracing the curve, but our formulation goes all the way through. So we're able to continue the movement through the entire device. And it's kind of interesting, at least to me. You can actually see how this thing is doing the calculation, which is on this serial chain. We did the best we could to compare the count of bars in this formulation versus ours, and the best that we get is ours is some fraction, something a third to a half the number of bars, depending on how you count the bars. I tried to count every one of the gears and everything. So our worst case, we don't really simplify this. Well, we simplify it in the sense of that you can see what's going on, but we don't actually reduce the part count in a significant way. So let's think about this path planning issue. If you go back to how engineers drew curves to the same period of time as that mechanical computer that's used, by the way, for computing trajectories of artillery on battleships, you can actually find mechanical Fourier analyzers. So this mechanical Fourier analyzer is designed from a series of what are known as Scotch yoke mechanisms. Not a complicated device. It's a pin that rotates in a circle. You just pull off the component that you want, either the cosine or the sine, depending on the phase, and then you add it with a belt. And these were used to, well, they were in the late 1800s all the way through the 1900s. They were used to do harmonic analysis and actually harmonic synthesis as well. So what you can do is that you can, from the equations, if you can get a Fourier series approximation of the equations of the algebraic curve, that means you need a parameterized algebraic curve. So I need x component and y component. Your general algebraic curve cannot be decomposed that way globally, but they can be decomposed that way locally. And then you get a Fourier series approximation to it. You truncate the Fourier series, and you can now draw the curve. So what's happening is that we are imposing constraints on the types of curves that we can draw mechanically. What's interesting is that you can take a somewhat arbitrary curve like this Batman logo, which is generated with about 3,000 points. You can do a discrete Fourier transform, truncate that. We truncated it to about 19 terms, and you get a mechanism that looks like this. And again, we've got one set of linkages that is drawing the x-coordinate, another set that's drawing the y-coordinate, and then they're coordinated so that they draw the curve. You can't see it that well, but this curve is not symmetric. Certain portions of it are shaped slightly differently. Say this, look at this peak here. This peak does not match that peak because of the inverse Fourier transform and the truncation. So we don't get all of the high frequency resolution. So I'm going to take a minute and do a little bit more history. Okay, this is another one of the examples that you can find that shows Kempe's linkage. Now in the 1960s, out of Russia came this particular book called Mechanisms for the Generation of Plane Curves. And this really took the approach that most all of the kinematicians had taken sort of since that time, which is that if you want a particular curve, design the linkage that matches that curve, okay? And what he did is he presented a whole, he mentions Kempe's approach, but he says that's really going to be complicated. Let me show you classes of mechanisms that will draw sort of the most useful curves that he could imagine. And it's a very nice book. I would only say this one problem. He presents this device to draw this curve right here, which is called the Trifolium. All right, it's very complicated with Kempe's approach, not a surprise there. But what's really surprised me is I said, okay, well, let's just use his linkage because it should work. It looks simpler, it should work. But what we found is that it doesn't work. Now, this is it. I don't know if we can get a bigger version. Yeah, what happens, and I'm sorry that you can't see it that well, but these sliders cross over each other in a way that this particular slider, this thing right here, has to float in space. So whereas he's presenting this as a very nice design for a linkage that draws a trifolium, as far as we can figure out, it simply doesn't work. Okay, but watch this mechanism. Well, this turns out to be no surprise. This, if you think about this, this is the representation of a Fourier series as a collection of epicycles. We've known this since Ptolemy, that we could approximate arbitrary curves in space, periodic curves in space, with this type of structure, okay, known as an epicycle. So this is an epicyclic chain. It was actually sort of the inspiration for us that was actually done by Venkat Krobi working for Vijay Kumar back in the early 90s. And they were designing linkages that had this, what they called coupled serial chains that would generate these curves. All right. This is a well-known curve. It's known as the butterfly curve. What we did is we expanded it in the Fourier series and truncated it to, I think, 14 terms here, and then designed this coupled serial chain that draws the curve. So this shows that we have what you would hope out of the theory of Fourier transforms actually works. Part of the inspiration for this was I think the somewhat bogus but interesting animation online that shows Homer Simpson being drawn by a coupled serial chain. At least it claims he's being drawn by a coupled serial chain. I cannot find anything anywhere that they show that it's actually done that way. But it's fun to watch. But this is actually just a series of epicyclic gear trains. In this paper, we show how to calculate the lengths of the links, the gear ratios. It turns out that these gear ratios are in many cases are non-standard, and therefore the best thing we could do is actually try to build them with additive manufacturing. So here it is. That's it, moving. We did the best we could. We matched all the gears as best we could. We made the ABS as stiff as we could, but just the slightest little bit of manufacturing error introduces backlash. And it's really what you're seeing is sort of the thing is about this tall. It just gets a little bit of wobble, not a lot, but just enough. And so whereas we can get dead on with this trifolium, this spacing here for our butterfly linkage is about the best we could do. And that's, but it's, I was quite pleased. We got pretty close. Now, at this stage, we realized that we could draw any curve that can be represented by a finite Fourier series. This is known in the literature as a trigonometric curve. What's surprising is that it's also known that there is a trigonometric representation for Bezier curves. So if you take a Bezier curve and represent it as a trigonometric curve, we can now design a mechanism that will draw it. And what I'm showing you here is the sort of standard representation of a Bezier curve that has this parameter in it that you can use to actually change its shape. It provides a slight change in shape. And what we'd use is that parameter. We would use that parameter so that we could actually reduce the complexity of our linkages. So here's an example. Now, the reason why we have this is that Kempe's result that there is a linkage that draws any algebraic curve was sort of presented colloquially in various talks and literature as Kempe's theorem proves that there is a linkage that will sign your name. The assumption there is that your name can be approximated by finite algebraic curves, and therefore the sequence of linkages that draw those algebraic curves will sign your name. So this is my student's name. That's my handwriting. Okay, and here is the linkage that draws it. What we did is, you can see we have 8 Bezier segments. Each has a linkage that consists of 6 links. The result is that an nth degree Bezier curve has a 2n linkage that draws it exactly. What we can do, however, is we can actually simplify those Bezier curves and draw them with links that only have 2 joints. Okay. So we just do it in reverse. Most everyone who looks at it sort of looked away at some point. So we draw it in reverse just to help you see what's going on. What's happened is I've got a different linkage for each of these segments. So the count here is really straightforward. I've got 8 segments and 4 links, 6, I'm sorry, 1, 2, 3, 4 links. Therefore, I have 32 bars, which is far less than anything that's been done up to this point. We didn't want to stop there. This is it turns out Chinese is typically a block printed language. So all the characters that you've seen in Chinese are written in block characters. However, there is a tradition in Chinese where you write in cursive. In fact, many Chinese are learning that tradition because that's how they write now on their smartphones. And so this is the script, or the cursive version of the Chinese character long, which means dragon. And so we were able to draw this with 8 linkages, Bezier segments with 4 links per segment. So we're doing 4 links instead of 6 because we're able to use that parameter, that lambda parameter, to shrink one of the sets of linkages down to be a very small size so that we can ignore it.
Is there ever a problem with these linkages locked?
All linkages lock, right? No, let's put this. I always have that problem. If the linkage locks, it's not useful to us. Do you know what I mean? So one of the procedures that we go through when we analyze these linkages to make sure they do not lock, or jam is what we say. Okay, so in this case, these guys are layered. We can make them that way. But you can obviously see they'll run into each other, so they have to figure out how to. We haven't solved that problem yet. But for example, all the walking linkages you've seen, any linkage, by the way, you might as well know that anytime you've got a sequence of 3 joints, the joints will have the elbow up and elbow down solution, always. And it can be that when you are moving through your discretized task, that to get to one set of task positions, you're in elbow up, and the other set of task positions, you're in elbow down. That is an example where the linkage would have to lock, and it would be useless because it can't get through that position. It would be locked at this position. So when we detect that, we get rid of that linkage.
What about reversibility?
What's that?
What about reversibility? So all the linkages reversible all the way, maybe related to what you just linkage. Because some of our linkages are not reversible.
Oh, reversible. Oh, yeah, yeah. We actually, every one of our designs, so we'll do, for example, when we do the 6-bar linkage, we'll get maybe, get say 20,000 solutions. We have to analyze every one. And what we want to make sure is there is a range of motion that includes the task position. It will be reversible in that range of motion. If it's not, we throw it away because that meant it went through one of these locked positions. In the other, the only time we worry about the complete rotation is if we're trying to use it for a walking machine. Okay, so that's the way that, and so when we analyzed them for the walking machine, we made sure that they went through complete rotations. Okay. That's an after the calculation evaluation step. All right, so what I'd like to show you now is other applications. We can do wings instead of legs. Okay, so this is a, we got this data from Tobowski and Dial. They did a whole high-speed video analysis of the black-billed magpie. We determined the trajectory. And from that, we determined the, so we would model the trajectory as a 2R chain. But this is now a 2R chain that moves in 3 dimensions. Okay, so there's 2 revolute joints here, and there's a revolute joint that goes this way, a revolute joint that goes that way, and then an elbow joint here. So this is 3 actuators. So we'd use that to trace the trajectory, the wrist point. This traces the wrist point. And then there's also a actuator on the end that's the end effector. So we have 1, 2, 3, 4 actuators, just like in the magpie. Now, just to give you a heads up of what we're doing, we now, from that, we did the inverse kinematics for the system and determined what would be the control signals that we would have to apply to obtain the joint trajectories that we wanted. So, and we tied all of those to a single input. So I have, in other words, to drive this joint for the same input, I would have to have the blue curve. All right, so now let me get this right. I'd have to have the black curve. The black curve is the required signal. And then same way here, same way here, same way here. So I want a single input that's going to generate these 4 outputs so that this wing traces the curve given for the black-billed magpie. Then what we do is we sample it like we did before. We take 11 locations on that curve, and we calculate the curve that will achieve that movement. We calculate the linkage that will achieve that input-output function. And what we get is this. So there's one. So these are 4 different linkages. Each of them goes through a full rotation, and they generate the periodic functions that define the angles of that wing. And this is what we get. All right, so we now have, this is about as cyberpunk a robotic system as you can get. There's a single input, and that single input is driving each of 4 mechanical calculators that are rotating the joints through cables of that wing. Now, it's kind of interesting if you look at the statistics. So out of the calculation, we got 11,000 linkages. From those, we analyzed them all, and we tried to make sure that they would go through a complete rotation and would not lock or do anything. And what we get is we got 6,000 of them, but none of them hit all the 9 points. All right? Now, the issue here is what's more important to me, that I get a curve that's close to the movement or that I get the exact curves I wanted originally. And so this is where we discover is some of the hardest aspects of the design. We can solve the problems. We can check the calculations. But the weak link is exactly asking what you want your mechanism to do, because we require a very precise mathematical prescription. But if, what you can find is that there's no mechanism that meets that requirement. When we looked at how far off it was, we found out that it was very close, and it was fine for us. And then we get something like 200 mechanisms. Took 20 hours to do this kind of calculation. Let me give you another type of wing movement. All right, this is a colleague of mine at the University of California, Irvine, who is studying the aerodynamics of hovering vehicles. So one of the things that they know about, it turns out that the nano hummingbird, which is so famous because it was flying around with a camera on it, maintained its pitch. So when you're swinging back and forth, you want to change the pitch of the wings so that you get lift. The way the nano hummingbird adjusted the pitch was by the material properties of the wing itself. They spend quite a bit of time determining material properties that would take the right shape when the wing was moving in an air environment in the proper way. What my colleague said, that look, if we didn't have to rely on the material, if we could actually actively position the pitch of the wing, we could actually get much more efficient flight. So what we did is he gave us the equations for it, so we designed a mechanism that did it. So here's the mechanism. This particular mechanism moves in a plane, but it's got this link here that's sort of an out of plane link that controls the pitch. And it turns out that this works very well in simulation. Okay, this is why I was warning you. Our manufacturing capabilities are a little bit weak. Oops, oh, it went by so fast you don't even get to see it. Let's see if I can. All right, so watch. So this is the linkage here. We have to do a better job. What we're finding is that we need to do better. Rapid prototyping is not serving our needs as well as we would like. But it does make the movement we want. It's just a little bit jerky. So it needs a little bit more design. A little more someone paying attention to the practical aspects of design, such as packaging, motor powering, better bearings, and things like that. All right. Spatial mechanisms. Most of what I've shown you here has been planar mechanisms that can be built by layering them up on parallel planes. The real benefit to computational invention like this is when you can design a mechanism you just cannot conceive of in any other way. And that turns out to be the characteristic of these spatial mechanisms. These are the precursors, frankly, to robotics. It was colleagues who were trying to design spatial mechanisms who came up with, for example, the Denefit-Hartenberg formalism. They came up with the practical techniques for solving kinematics equations. The decision to work on a purely open chain where it had 6 degrees of freedom rather than 1 degree of freedom turned out to be an enormous simplification of the problem. It was a great step forward. We could actually work in 3 dimensions with using control theory combined with kinematic synthesis and analysis. But we did have to pay the penalty that we had to work with higher degree systems. So what I'm going to show you here is solving the same problem, but we're going to solve it with a spatial mechanism. It's a spatial 6-bar linkage. The benefit of it is that it has an enormous advantage in terms of packaging. Fits into the space in a very convenient way. Yet it is almost impossible to visualize its movement. So let me try to show you if I can help. So this is the pieces coming together. I had a undergraduate student who I spent all the money I could on getting the graphics capabilities he needed, and he just went crazy. But the part I can't get rid of is the sound. So please ignore the sound. So this is the device that now does exactly the same flapping wing movement. We're trying to build that as we speak. We have several different versions of it. It's going to take us a little bit of time. We just have to get better at manufacturing. Another interesting application for this spatial mechanisms is in the tunnel boring world. It turns out that a tunnel boring machine has to inject foam into the as it's rotating and cutting, it has to inject foam to sort of manage the dirt that it's cutting up and moving away. And and that's very high pressure, very caustic foam. And it turns out that it has a standard problem that those ports, you can sort of see the ports here, for example, and in here, those ports clog. And so it's a constant calculation in a tunnel boring machine, how long I've been doing the boring and at what point I'm going to stop so that I can clear the percentage of ports that I know are clogged. That's an enormous task. We came up with this design working with a colleague in Germany who's in the tunnel boring business. So those are the soil conditioning ports. I guess I have to warn you that it is hard to look at this mechanism and figure out what's going on. What it's doing is it's plunging and then opening this mechanism. So it sort of rotates, plunges in order to close the port. It comes out and rotates open in order to open the port. And it's doing it in response to line pressure on this plate. So essentially what you do is you open the pressure pushes on that plate and it opens the port. When you close the hydraulic line, that reduces the pressure and the port closes. Did I say that in reverse? You turn the line pressure on, it opens the port. Turn the line pressure off, it closes the port. Okay. All right. Now that's really the end of my story in terms of my research. But I actually spend a lot of time with students doing design work at the undergraduate level, and these are at the high school level. I like to think of them, I'm doing research in tools for invention. These are the students who are going to be doing that invention. And what you see here is it was raining. It was my energy invitational. We have a competition that we put together where students drive cars, and instead of trying to save gas, we want them to save energy. We want them to drive fast, but we don't want, and so what we want them to do is use the energy wisely. They drive on a course for an hour, and they're allowed to use $1 worth of whatever energy they want. Okay, the most recent car won because it had solar arrays that gave it just a couple fractions of a cent of energy, and it was enough to help it win. Okay, I just want to give you a little bit of flavor of what that's about. So this is our UCI Energy Invitational. This was from 2000. Well, this isn't this year. We just completed it, so I don't have the video. But this is from a previous year. So if you don't understand this style of video, I didn't either, but it turns out that it mimics what's very common on Instagram these days. And I don't know if anybody believes me, but that's what I was told. So these are high school students building these race cars. I do get my UCI team out there. So my UCI team gets out there with their car and competes against them. We used to win, but now we seem to always come in second, and I can't quite understand what's going on. That's one of our race cars. Okay. Those are my students on the course. They help manage the entire event. And that's it.
What's the power on that? Powertrain?
They can have whatever powertrain they want. So most of the high schools go with a electric car that's built on a utility vehicle. Okay, so the campus sort of small utility vehicles, oftentimes they're electric. That's what they'll use. They'll strip it down and then they'll put a body on it. And we have the manufacturer of those utility vehicles. He'll come in and he'll adjust the performance of them, get a little bit of a boost. So it's pretty interesting. Path synthesis. So these are mechanisms that draw an arbitrary path. There's these two classic ways of doing it. They both have got limitations, but we're making good progress. Kinematic synthesis of robotic systems, I think, provides us some versatility in terms of the kinds of devices that we can build and use. Spatial mechanisms really is, we're coming back to it. I started out, just so you know, when I was here originally at Penn, Norm and I submitted a proposal to NSF that was funded because we were using a silicon graphics machine as a three-dimensional graphics workstation, graphics drawing board for spatial mechanisms. Norm, I've had to backtrack a long way before we could get there. I think we might want to think about it again. They might go for it again. Anyway, so coming up with a practical design system for spatial mechanisms is really a significant challenge. They have the benefit of having very nice performance. They couple in very nicely with robotic systems, and I think there's some great opportunities. Anyway, thank you very much for having me.
So the Bezier curve drawer. So
Yeah.
it's one linkage per segment.
Yes.
Of that.
Yes. Four links, and it'll draw most of the Bezier curves. It has to have a pretty high frequency component to not be able to draw it. Cubic curves typically don't have that high of a frequency component.
So if you wanted to do this with one real mechanical linkage, you have to accomplish two things. One is the lengths of the links need to be variable.
No. If I can draw if you draw the curve with a single Bezier curve, right, of whatever degree you need to draw that curve, that can be drawn with a single link. It just is twice the number of links is twice the degree of the Bezier curve.
Okay, but you had like 8 segments.
Because I wanted them all to be short. You see what I mean? Typically people use a cubic Bezier curve. Nobody knows how to draw, a 10th degree Bezier curve, right? So, but you could in theory. But in answer to your question, if you draw an arbitrary curve with segments of cubic Bezier curves, you now need these individual links.
Right, so that's what I'm saying. So if you made a reconfigurable link length,
Oh yeah.
you somehow could like move the fixed point along.
You have to, unfortunately, you have to change the speed ratio too. Okay, so, but it may not, no, the speed ratios may be, you might be able to manage that. You're right, so you could do it with changing the link lengths. That's right, you could exactly do it that way. Yeah. So we could just take one and we would adjust it. And that goes for all of our devices, frankly. I mean, we impose the requirement that our links be a fixed length, but what we've discovered is that one of the things that you find is that you want to have some sort of adjustment, right? So, for example, we've been designing knee braces that track a particular trajectory, and we got very close to that trajectory, but we had one point that was kind of off. There's kind of a lobe that was misplaced. And rather than redesign the whole thing, we said, is there anything changes we can make to this particular device to bring that nose lobe down? We took that linkage, put it in an optimizer, right? Because I can now take the same curve and just adjust it slightly. It turned out that it was a very small adjustment of 2 of the dimensions. Actually, it was a small adjustment of the placement of a fixed pivot that corrected that. So there is a surprisingly amount of room for getting more versatile devices by adjusting the devices that we design. And we haven't even had a chance to explore that. Yeah.
Okay.
Am I running over time?
I think we need to vacate a room.
Okay. Thank you very much.